Welcome. In this video, I have yet another example of a convergent or divergent sequence that's left for us to determine. And if you've been watching the videos in order, this is definitely going to be the trickiest one you'll see. So we want to consider this sequence of 1 plus 2 over n, and this entire quantity to the nth power. So let's take the limit of this sequence as n approaches infinity. Now this limit is a little bit involved, so we need to do some side work here. And what am I going to do in the side work? I'm going to do a little bit of tricky ninja algebra. I'm going to say that y equal 1 plus 2 over n to the nth power. Then the natural log of y equals n times ln of 1 plus 2 over n. And this next part is pretty ninja. If you notice, e to the ln of y equals y, since of course the natural logarithm and e are each other's inverse, so we just end up with y. Well, how is this going to help us with our limit? Well, I'm going to rewrite this as the limit, and we still have n approaching infinity of y instead of this. And that's because here I said let y equal this entire quantity, or this amount that is my sequence. Then I can rewrite this as the limit as n approaches infinity of e to the ln of y. Next, we can rewrite this as e to the limit as n approaches infinity of ln of y. Well, what is the ln of y? If you remember from our side work, ln of y is equal to this amount here, n times ln of n times the natural log of 1 plus 2 over n. So we just need to figure out what this limit is, or what this quantity is, e to this limit. So let's just look at this portion separately. And I'll make it blue so we can definitely, or actually what color would be better? Let's make it green so we can distinguish it from the rest of our work. So this is the limit we're interested in. But we have a bit of a problem here. As n approaches infinity, we end up with an infinity here times, and then this natural logarithm will approach ln of 1, which is 0. So we end up with a case of infinity times 0, which is an indeterminate form. So we're going to need to rewrite this in a manner that we can use L'Hopital's rule. And this is from Calc 1. So if you're a little rusty on L'Hopital's rule, I would quickly just Google it. Pause the video and Google it if you're rusty. Otherwise, let's keep going. So let's rewrite this as the limit as n approaches infinity of the natural logarithm of 1 plus 2 over n divided by 1 over n. And we have not changed a thing. We've just used our ninja algebra to rewrite n as 1 divided by 1 over n. These two expressions are equivalent. Now we can apply L'Hopital's rule directly, and we take the derivative of the numerator, which is 1 over 1 plus 2 over n, times negative 2 over n squared, and divide by negative 1 over n squared. The derivative of the natural logarithm is just 1 over the inner argument, and since the inner argument here is a function, we take the derivative of that due to the chain rule, and then the derivative of 1 over n is negative 1 over n squared. And I forgot my limit notation, so let me go ahead and fix that. Now that that's fixed, I can write this as the limit as n approaches infinity of 1 over 1 plus 2 over n times 2 times negative 2 over n squared times n squared over negative 1, which simplifies to this 2 divided by 1 plus 2 over n, and we're taking the limit of this as n approaches infinity. As n approaches infinity, this quantity will tend to 0, so we end up with just 2 over 1, or just 2. Now that we have this limit completed, I'm going to scooch this work down and replace this portion here with the value of the limit we computed below. So this just becomes e squared. This tells me that not only is this sequence convergent, but its limit is e squared.